Today we are going to determine the moment capacity of a beam, of a composite beam section. And the question says or asks, determine the moment capacity of the section shown in the figure below, assuming that the beam is made of grade S355 steel. Also, design shear connectors, assuming the beam is 6 meters long and that full composite action is to be provided. So we have a composite beam section with a concrete flange and a steel beam section that is in form of an I section. The serial size of the steel section, that is the universal beam section, is 46 by 178 by 74. The effective breadth of the concrete flange is 1500 millimeters, whereas the depth of the concrete flange is 130 millimeters. We are going to begin by calculating the resistance of the concrete flange. Therefore, the resistance of the concrete flange, that is RC, resistance of the concrete flange, resistance of the concrete flange, that is RC, will be given by this formula. RC is equal to 0.45 FCU multiplied by cross-sectional area of the concrete flange. In this case, FCU, that is the characteristic strength of concrete, is 35 newtons per square millimeters. I had forgotten to include it there. Therefore, the resistance of the concrete flange will be given by 0.45 times characteristic strength of concrete, that is 35 newtons per square millimeters, multiplied by cross-sectional area of the concrete flange, which is given by effective breadth of the concrete flange, that is 1500 millimeters, times the depth of the concrete flange, which is 130 millimeters. And therefore, that will be times 1500 times 130. We are going to get the answer in newtons, but we can convert to kilonewtons by dividing by 1000 or multiply by 10 raised to the power of -3. And when we do so, we are going to get a resistance of 3071.25 kilonewtons. That is 71.25 kilonewtons. After doing that, we are going now to determine the resistance of the steel beam. And therefore, the resistance of the steel beam, that is RS, resistance of the steel beam section, RS, will be given by the following formula. Therefore, RS will be given by design, that is the area of the steel section, that is area of this steel section, and that one can be obtained from Appendix B of the BS 5950, which happens to be 95 square centimeters. Then we multiply by the design strength of steel, which in this case is 355 newtons per square millimeters. Since from table 4.3 of the BS 5950, the thickness of the flange is 16 millimeters. Therefore, with a thickness of 16 millimeters, the design strength of this steel will be 355 newtons per square millimeters. Therefore, the resistance of the steel section will be area, which is 95 square centimeters. We convert to square meter. We multiply by 10 raised to the power of 2 times 355 newtons per square millimeters. We convert to kilonewton per square meter. That is dividing 355 by 1000, or times 10 raised to the power of -3. And therefore, the resistance of the steel section will be equal to 3372.5 kilonewtons. When we now compare the resistance of the concrete flange and the resistance of the steel beam, we find that the resistance of the concrete flange is less than the resistance of the steel section. And therefore, this means that the neutral axis will fall in the steel flange. And we can prove this by calculating the depth of the neutral axis. And the depth of the neutral axis will be given by RS minus RC divided by 2 times breadth, the width of the steel section, times PY, which is the design strength of the steel section. And therefore, this will give us RS, which is 3372.5 kilonewtons, minus RC 3071.25 kilonewtons. We convert them to newtons by multiplying by 1000. Therefore, times 10 raised to the power of 3 divided by, the reason as to why we are doing that is because the width of the section is given in millimeters, the design strength of steel, newtons per square millimeters. So we multiply by 2 times B, the width of this steel section from Appendix B of the BS 5950 is 179.7 millimeters times now the design strength of steel, that is 355. And when we do so, we are going to get the depth of neutral axis to be 2.4 millimeters. And therefore, that means that the neutral axis will fall in the flange of the steel section. Then from there, we are now going to calculate the moment capacity. So we go to moment capacity of the composite beam section, that is MC. And the moment capacity will be given by this formula, that is RS times D over 2 plus RC times DS over 2 minus RS minus RC squared divided by RF. Then we multiply this by the thickness of the section, that is T, divided by 4. So that is the formula of determining the moment capacity of this composite beam section, since the neutral axis is falling in the flange of the steel beam section. We are going first of all to calculate RF, that is the resistance of the steel flange, and the resistance of steel flange, that is RF, is given by B, which is the width of the UB section, multiplied by T times the design strength of steel. This is going to be equal to B, the breadth of that is the width of the steel section from appendix B. We had it somewhere, that is 179.7 millimeters, therefore 179.7 millimeters. We multiply by T, which is the thickness of the fringe, and the thickness of this fringe from table 4.3 is 16 millimeters, since the section is made of S grade S355 steel. So we multiply by the thickness of the fringe, that is 16, times the design strength of steel, that is 355. We are going to get 1.02 times 10 raised to the power of 6 newtons. Therefore, that is RF, the resistance of the steel fringe. Therefore, we can now calculate the moment capacity, and in this case, MC moment capacity will be equal to RS, which is 3372.5 kilonewtons. 3372.5 kilonewtons. We convert it to newtons, we multiply it by 1,000, therefore times 10 raised to the power of 3. We multiply by D over 2. D is the depth of the steel section obtained from appendix B, and it is actually 179.7 millimeters. We divide that by 2. Then we add RC, the resistance of the concrete flange, that is 3071.25. We multiply by 1,000, 10 raised to the power of 3, to convert it to newtons. Then we are going to multiply that by ds over 2, and ds, the depth of the concrete flange, is 130 millimeters. Therefore 130 divided by 2 minus rs, that is 3372.5, 3372.5 kilonewtons, minus rc. So we subtract RC, which is 3071.25. 3071.25. They are given in kilonewtons, and we must convert to newtons. Therefore, what we are going to do, we are going to multiply by 1,000, and then we square. Squared. We divide by RF. So divide by RF, which we obtained it here. It is 1.02 times 10 raised to the power of 6 newtons. Therefore, divide by 1.02 times 10 raised to the power of 6 newtons. Then we multiply by T over 4, whereby we have said that T is 16 millimeters from table 4.3 of the BS 5950. Therefore, 16 divided by 4. This is going to give us a moment capacity of 895.4 times 10 raised to the power of 6 newtons millimeters. We can convert it to kilonewton meter by dividing it by a million, since 1 kilonewton is equivalent to 1,000 newtons, 1 meter is equivalent to 1,000 millimeters, making 1 million. Therefore, the moment capacity of this section will be 895.4 kilonewtons meter. So we are done with the first part of the question, that is asking us to determine the moment capacity of the section shown in the figure below in grade S355. The next part of the question is designing connectors. And in this case, when it comes to designing connectors, we are going to determine what we call shear studs. So we go to what we call shear studs. Shear studs. And from table 4.18, the characteristic resistance, which is usually denoted by QK, characteristic resistance, that is QK of studs, having 19 millimeters shank diameter by 100 millimeters height. 19 millimeters shank diameter, 100 millimeters height. It is something like this, just to explain in layman's language. This is a shank whose diameter is 19 millimeters, and this is 100 millimeters high, a height of that stud of 100 millimeters. So from table 4.18, with such a stud, the characteristic resistance in grade 35 concrete of such a stud is 104 kilonewtons. That information, you obtain it from table 4.18 of BS 5950. And therefore, the design strength of the studs, design strength of studs, that is QP, will be given by 0.8 QK. Therefore, the design strength of the studs, that is QP, will be given by 0.8 times QK, that is the characteristic resistance of the studs, which is 104 kilonewtons. Multiply that by 104. That is going to give us 83.2 kilonewtons. From that, the number of studs that are required in this case will be given by the resistance of the concrete flange divided by QP, which is the design strength of the studs. And in this case, the number of studs will be equal to RC is 3071.25 kilonewtons divided by QP, which is 83.2 kilonewtons. And this is going to give us 36.9 studs. This number should be greater than that, so we can approximate to an even number of 38 studs. Therefore, we are going to say this: provide 38 studs evenly arranged in pairs in each half span of the beam. Therefore, ladies and gentlemen, that is the end of our today's lesson, and that's how we go about this particular question that we got here. So thank you very much for watching our video. Please do subscribe. This is George Kamiti. See you in our next lesson.